Hello guys, welcome to Self Help Maths Academy. Today we're going to talk about eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So let us start understanding the definition. What do you mean by eigenvalue? So first of all, um, an eigenvector, an eigenvector of an n cross n matrix A is a non-zero vector x such that ax equal to lambda x for some scalar lambda. Okay, so here what we are trying to understand, what is the eigenvector for any n cross n matrix. So here we are talking about any square matrix. Okay, it has to be a square matrix, n cross n matrix A. It is a non-zero vector x. Okay, eigenvector is a non-zero vector x such that when I multiply the given matrix, a square matrix A, with that non-zero vector x, if I am able to express that as some lambda into lambda times of x, if you observe, if I am able to express A in times of x as lambda times of x, where lambda is any scalar, so this lambda belongs to any scalar, it is any the real number, if you consider. Okay, it is any scalar, then we call that x, this x, as eigenvector. Okay, and a scalar lambda, this scalar lambda, we call it as eigenvalue. So basically this this lambda is called as eigenvalue of a matrix A if there is a non-trivial solution x of ax equal to lambda x. Okay, so then we call that lambda as the eigenvalue and corresponding vector x as the eigenvector. So basically when we are applying this particular lambda or the eigenvalue lambda. Okay, so by applying a to the a to this x, by applying this a to x, only scales our the given matrix by the lambda. If you see, it is scaled by lambda without changing its direction. So basically eigenvalues, they represent the fundamental properties of our matrix, and they are very crucial in very various applications. All right, especially we use it in our quantum mechanics, in principal component analysis, where you're using the dimensionality reductions. Okay, so all those things. So let us understand now in detail this particular topic with the help of example. So let us see the example here. If I have, say, let a equal to, they have given as 1,652, and they gave us some u, which is say 6 and -5, and they have given you some v, say 3 minus 2. So the question here is, are this u and v are eigenvectors? Are this u and v are eigenvectors of capital A? This is the question. So they have given us with the two vectors. And they ask us to find out whether those two vectors are the eigenvectors of the given matrix A or not. So just now we have understood the definition. When we say that as eigenvector, the x is said to be eigenvector only when if I'm able to express A into x as some lambda into x, where lambda is any scalar, right? So if this is possible, then only I'm able to say that that is my eigenvector. So let us consider now. Let me take A and let me take u. If I'm able to express A into u as some lambda times of u, then we will check whether we are able to do that or not. So this is our 1652 and u is 6, 5, 6 negative 5. So here we multiply with this is equal to 1 times of 6, 6 times of negative 5, which is negative 30. This is 30 here, minus 10. So which we are getting as minus 24, and here it is 20. Okay, so in both the case, if you observe, I think I can take 4 as common in both the rows. So this, if I take, it will be minus 6 here and 5. So this is still, if you see, minus 6, 5 is my vector u. So I can write this as 4, I have to take the negative 4. When I take negative 4, so this will become positive and this become negative. So this will be negative 4 into u. So carefully if you observe, this is nothing but like, in the format of lambda times of u, where I have my lambda as negative 4, right? So therefore I'm able to see that I have expressed this as this particular a into u as lambda times of u, which is nothing but negative 4 times of u. All right, so hence we say that the u, now clearly u is an eigenvector. Okay, this is an eigenvector. Now similarly, let us check whether the v becomes the eigenvector. For that we have to check a into v. So for that we will take the matrix A, that is 1652, and we'll take v, which is given as 3 minus 2, which is equal to. So this is now equal to 1 times of 3 minus 12. This is 15 minus 4, right? So which is equal to, here we get minus 9. Let me write it down. This is equal to, yeah, minus 9, and this is equal to, say, 11. Yeah. So here, this minus 9, 11, we cannot express as some lambda times of the vector 3 minus 2. So this is not possible. So this is not possible here. Okay. So this is not possible here. So hence this v, the vector v is not an eigenvector. Okay, this is not an eigenvector of A, of the matrix A. So clearly what we understood is whenever we want to check whether the given vector is an eigenvector or not, we have to multiply that vector with the given matrix, and then we have to check whether I'm able to express that as a scalar multiple of the given vector or not. If it is not, then it will not form the eigenvector. So similarly, I think one I'll give for you. So please try and comment the answers. You should comment in the box. So let me give you one example for you. That is, you take A as say 3, negative 2, 1, 0, and check whether u is equal to negative 1, 1, and v is equal to say 2, 1. So which one of them will be an eigenvector of A, or both of them will be an eigenvector, or one of them will not follow, whatever it is. Please comment in the box so that we will check, okay, which one will not form the eigenvector. So now let's see little different examples. Let me see this one. Show that say whether 7 is an eigenvalue. Is it an eigenvalue of the matrix say A equal to 1, 6, 5, 2, and find the corresponding eigenvector. Find the corresponding eigenvector. Okay, so this is the question. Let us check how do we deal with this. So they ask us to check whether this 7 will become an eigenvalue of this matrix or not. So to become 7 can be eigenvalue. 7 to answer this question, 7 is an eigenvalue of A, eigenvalue of the matrix A when, if and only if I'm able to express A into some eigenvector, say, which I don't know, x, as lambda into x, where lambda is what? Eigenvalue itself is given as, say, x. If I'm able to write this as ax equal to 7x, this has a non-trivial solution. Has a non-trivial solution. When I say non-trivial solution, means it should have the solution other than 0, because this said if you take x as 0 0 0, it actually obviously satisfies the equation, but we have to have a non-trivial solution which should be other than 0, then we call it as a non-trivial solution. Okay, so it should have a non-trivial solution. In otherwise, like this is the same thing, we can write it as ax minus 7x equal to 0. This is a homogeneous equation if you observe. Or we can also write this as a, okay, minus, because this is a matrix, A is a matrix here. So when I'm taking this x vector common, so here I'll be getting A minus 7i identity matrix times of x equal to 0. Okay, so this is how we will write. So please try to understand here. You have got ax equal to 7x. We can write this as ax minus 7x equal to 0, where A is the matrix, x is also the vector, okay, and then 7 is the eigenvalue and x is the 7 is a scalar, basically it's an eigenvalue, right, and x is the again vector. So we can write this as A minus 7 times of I, where when I multiply with identity matrix, again there will be no change, so therefore you have to remember that it has to come in this way. All right, now to solve this homogeneous equation, what we do is we will try to form the matrix here. If you see, this is our matrix, this we have to augment with this 0. If you the basic idea is here, if you consider the whole thing as, say, some b, and like this is like x equal to 0, so then your augmented matrix will be b augmented with 0. Now in place of b, what I have this, so hence your augmented matrix will be like now A minus 7i, this you have to augment with 0. This should be your matrix. Okay, so this is the basic understanding we have to have. So now let us see, let us do this one. Let me take the matrix A and I'll do this whole thing. Now let me check, this is like, say, A 1 6. We will do it in detail because this is the first matrix. So this is our A. Here let me show you how our A minus 7i looks like, and then we will take this augmented matrix for the first example. This is our A minus 7, because it is a 2 cross 2 matrix. Take our identity matrix is also of 2 cross 2 order. All right, so now this will be equal to 1 6 5 2, and minus, here if you take, this is 7 times of 1 is 7 0 0 7. Okay, so in short, if you see, this one is like 1 minus 7, 6 minus 0 is 6, so 5 minus 0 is 5, and 2 minus 7 is 7. So basically in the coming examples we will try to see, it is just these diagonal elements will be subtracted by the eigenvalue. If you observe, see, 1 minus 7, 2 minus 7, remaining both the elements are as it is, right? So in the next example onwards, we will not do these whole steps in detail. We just go straight forward and we'll try to do it. Like now you have got your A minus 7i as, this is the negative 6 6 5 and negative 5. Okay, now as I told, I want this augmented matrix. So let us take this augmented matrix, that is A minus 7i augmented with 0. This will be now minus 6 6 5 minus 5. This we have to augment with 0. Okay, so next example onwards we will directly come to this particular step, rather doing those steps. Okay, so now finding in order to check that this particular these particular the system has a solution or not, we have to check whether it has a non-trivial solution or not. So let us check that first. So what I'll do from the R1, from R1, from R1, let me take from R1, let me take one negative 1 by 6 times of R1, and from R2 1 by 5 times of R2, just to make it simple. So therefore this we will get it as 1 negative 1 0. This is 1 negative 1 0. Okay, now use the row operation. Say R2 changes to R2 minus R1. So this gives us 1 minus 1 0 0 0 0. Clearly from the second row, if you observe, this is x1 minus x2 equal to 0, and from 0 equal to 0 means here it is free. Okay, so that means x1 equal to what? X2, and your x2 is free variable, right? So when you write a solution now, so therefore the general solution, if you write x equal to your x1 x2, okay, this is equal to your x1 is what? X2 here, which is x2, and x2 is free, so I can write that as x2. So this one, if I take x2 out, here it is 1 1. Okay, so here if you see that if I don't have, with each values of the form with x2 cannot be 0, will become an eigenvector for a corresponding eigenvalue lambda equal to 7. So what you have got here, since if you observe carefully, from this we understood that the columns of the a minus 7i, this one, from this columns of a minus 7i, we observed obviously they are linearly dependent. If you see minus 6 by 5, I can write it as a scalar multiple of 6 by minus 5, right? So these are the dependent columns. So therefore it actually talks about the non-trivial solution. It has a lot of solutions here. Okay, so when you see that it has a free variable, so it has many solutions. So when it has many solutions, I told you, I started with this only. I told you this particular equation should have a non-trivial solution. So clearly we understood that it has a non-trivial solution. Therefore lambda equal to 7 becomes the eigenvalue. So here we decided that when it has a solution, when it has a non-trivial solution, see, with the x2 as a free variable, we have got many solution. As you put the x2 value, you'll get infinitely many solution. So therefore it has become what? It has become eigenvalue. So now to find out the corresponding eigenvector, we continued and we wrote a solution. So if you see, with the free variable, you have got this vector. As you just keep changing the x2 values, you will get infinitely many vectors. So now these vectors, this vector with this, for example, one vector with x2 equal to 1, say 1 1. If I take x2 equal to 1, okay, then this will become one of the eigenvector corresponding to the eigenvalue lambda equal to 7. Okay, so therefore here we proved both the things. So lambda equal to 7 is an eigenvalue. Also this vectors, which is by substituting the x2, which is not equal to 0. So any value for this particular x2 will give you infinitely many eigenvectors which are corresponding to the lambda equal to 7. Okay, so what is important here is, although this row reduction was not used in the above example, like say here in this case not much we have used to find out the eigenvector, so it cannot be used to find out the eigenvalues. Okay, usually we try to understand the non-trivial solution part in order to check whether it is eigenvalue or not, and then we have to do the row transformation or the other methods also. I'll just show you one by one in order to get the corresponding eigenvector. Okay, so now from this I'll give you some two important notes. Okay, so one note is lambda is an eigenvalue. Okay, of any matrix A when, if and only if, this is very important, if and only if the equation a minus lambda I times of x equal to 0. So in this case, if you observe, a minus 7i times of x equal to 0, like that. Okay, so this equation has a non-trivial solution. Non-trivial solution, that is very important. That is one condition. Okay, so it has to have a non-trivial solution. Then second one is the set of all solutions. The set of all solutions of x is just the null space of the matrix A minus lambda I. So here if you observe it, like A minus lambda I times of x equal to 0, which is nothing but the set of all the solutions which are in a null space. So therefore the set of this x is nothing but what it is. It is just the null space of this matrix here. Okay, A minus lambda I. So this is a subspace of what we know that null space is a subspace of Rn. Okay, it is a subspace of Rn and is called eigenspace. It is called as the eigenspace of the corresponding eigenvalue lambda. Okay, so this is very important to know. So therefore we have the eigenspace, which is consisting of all the eigenvalues. Okay, and actually the eigenspace consists of even the zero vectors and all the eigenvectors corresponding to this eigenvalue lambda. In this case, as you substitute the value of x2, you will get infinitely many eigenvectors, right? All those eigenvectors are they're all in the collection of eigenspace. Okay, so that is also one of the important space. Like now, so we have studying null space, call space. Like we have now looking for this eigenspace. So these are the two important notes we have to know. Okay, so I think yeah, let me stop at this point. So maybe I think I'll give you one more a simple example for you all to check whether the given to check whether this will the similar example to find out check whether lambda equal to 9 is the eigenvalue of the matrix, say 2 7 7 2. Okay, check whether it is the eigenvalue of this matrix or not, and also find the corresponding eigenvector. Find the corresponding eigenvector. Okay, so I think answer me in the comment box whether you will get it as eigenvalue or it is not eigenvalue, and how many eigenvalues you will find basically for this. So let me check. Let me see your answers. Okay, so try this one, and maybe I think in the next video we will talk about the 3x3 matrix, and we will talk about the eigenvalues and eigenvector of the corresponding 3x3 matrix. Okay, so this is all in this video. See you guys in the next video. Till then, take care.